Group 1 present film dosimetry. Table of contents. Introduction. Type of film dosimetry. Dosimetric properties. Dose determination. Medical applications. Future direction. Introduction. A radiation dosimeter is a device, instrument, or system that can directly or indirectly measure or evaluate exposure, karma, absorbed dose or equivalent dose, their time, rate, derivative or related ionizing radiation. A radiation dosimeter must display several desirable characteristics. For example, in radiotherapy, it is important to have a precise understanding of the absorbed dose of water at a specific point and its spatial distribution and the possibility of deriving the dose of the patient's organ of interest. The desired characteristics of the dosimeter will be characterized by precision, accuracy, linearity, dose correlation or dose rate, energy response, directional correlation, spatial resolution. Concept. In radiation dosimetry, the use of conventional measurement systems such as ionization chambers, semiconductors, thermoluminescence detectors, TLD, and radial films to measure isodose curves and dose depth distribution in high beam gradient regions has several problems. Look at Table 1. These difficulties have led to the study of high spatial resolution radiation dosimeters, which do not require special development procedures and provide the absolute value of absorbed dose with acceptable accuracy and precision, easy processing, and data analysis. Table 1. Problems of conventional measurement dosimeter. Conventional measurement dosimeter, ionization chambers, and semiconductors. Problem: cannot provide sufficient spatial resolution for many treatment planning needs when a one-dimensional or two-dimensional dose distribution is required. Thermoluminescence detectors, TLD. The problem is cannot be used to store dose data for archival purposes because the sensitivity to photon energy in the 10 to 200 keV region varies greatly. Radial film. The problem is difficult to evaluate ionized photon beams using a radioactive silver halide films. Although the relatively high spatial resolution provide advantages over most other radiation measurement systems. What is the film dosimetry? Film dosimetry is widely used to obtain the relative dose distribution of clinical electrons beams in the hallucination formed by water, plastic, and heterogeneity. Film dosimetry is conducted to high spatial resolution and short measurement time. It consists of small box with a film placed between the filters. The sensitivity to radiation depends on the energy photon with the best sensitivity at the K edge of the film. A filters to evaluate the penetration ability of the radiation source, thereby providing an estimation of the photon energy. The film is post-processed, and the measured optical density provides an estimated dose based on the average energy of the photon. Film plates can provide permanent exposure records, which means they cannot be reused. In addition, it is reliance on photon energy, temperature, chemical limits its accuracy. Film is used for radiation measurement, especially for measuring relative dose distribution. However, the dosimetry accuracy of the film is limited to 2 to 5%. Types of film dosimetry. Radiographic film. Radiographic films are similar to films used in all radiographic applications and require chemical development. Chemical development increases cost and introduces significant changes in dosimetry. Radiochromic films. A radiochromic film is formed by polymerization. This self-imaging characteristic has led to the replacement of radioactive color film for dosimetry to a large extent. Radiographic films. Radiographic film construction. Plastic base provide the structure of the film. Silver bromide emulsion is the active layer of the film consisting of silver and bromide ions. Grains are 0.1 to 3 nanometer in diameter, 10 exponent 9 to 10 exponent 10 grains per square centimeter. Gelatin protective layers serves to keep the silver bromide grains well dispersed and to protect unexposed grains during development. Radiographic film principle. Radiation source hitting the dosimeter film into a radiographic film. Lose electron gather around the impurities, forming a negative charge. Negative charge attracts the silver ions, leaving neutral metallic silver. The latent image will be magnified 1 billion times. The latent image is composed of metallic silver atoms and cannot be seen without evolution. The latent form can consist of as few as 10 silver atoms. There are thousands of metallic silver atoms in the latent image because a single X-ray quantum can produce more than 1,000 silver atoms. Increases the amount of metallic silver and the underlying image. Use acetic acid called stop bath to stop further development. Read the film on a calibrated optical digitizer. Stabilize the image. The stabilizer, sodium thiosulfate, dissolve all undeveloped particles. Radiochromic film construction. Base layer. Polyester base provides structure to the film. Active layer. It is composed of radiation-sensitive chemical substances that will turn into an optically opaque polymer when irradiated. Gelatin protective layers serves to keep the silver bromide grains well dispersed and to protect unexposed grains during development. This is a chemical reaction that will take about 24 hours to complete, although most of the development occurs in the first hour. Principle of radiochromic film. The incident radiation on the active layer causes a polymerization reaction. When the active layer polymerizes, it becomes partially opaque in a proportion to the incident dose. This process takes several hours, and the time between measurement and reading must be controlled. After 1 to 24 hours, Read the film on a calibrated optical digitizer. It is possible to obtain close instantaneous readings, but will result in lower measurement accuracy.
Now I want to talking about advantage and disadvantage. For radiographic, dose accuracy 3 to 5% and radiochromic 2 to 3%. The advantage for radiographic, highest spatial resolution, energy independent in MV region only, and lower dose threshold. The advantage for radiochromic, tissue equivalent, Z equals 6 to 6.5, energy independent, no chemical processing, and very high spatial resolution. The disadvantage for radiographic, required chemical processing, increased cost of development, increased measurement error, not tissue equivalent, fogging invisible light, and strong energy dependence in KV region. The disadvantage for radiochromic required higher minimum dose around 0.1 gray. Now, isometric properties. Dose density dependence, no linear. Calibration is unavailable. A dose range convert around 0.2 millisievert to 3 around 3 sievert. Two film in one package. Type of radiation convert. Photons greater than 15 kiloelectron volt, electrons greater than 200 kiloelectron volt, and streamer neutrons. Energy dependence sensitivity ratio 15 to 54 kiloelectron volt for cesium 137. Fading less than about 15% in 90 days for high sensitive film. Less than about 20% for lower sensitive film, both for temperature range up to 30 Celsius and humidity up to 60%. And light sensitivity must be protected from exposure by light. Now a radiographic. Light emission is a function of film opacity and can be measured in terms of optical density using a special device called densitometers. The film offers excellent 2D spatial resolution and in a single exposure. I provide information on the spatial distribution of radiation in the region of interest or the attenuation of radiation by objects. The useful dose range of the film is limited. Energy dependence is evident for low energy photons, and the response depends on several parameters that are difficult to control. Films are usually used for qualitative dosimetry, but with proper titration, careful use and analysis. Film can also be used for dose assessment, and the important parameters of film respond to radiation area, gamma, attenuated, and speed, the slope of the straight part of the H and D curve in called film gamma. The typical H and D curve of radiographic film is shown in figure. It has four areas: 1 fog, low exposure or no exposure, 2 tools, 3 linear part of middle exposure, and 4 shoulder and saturation. At high exposure, the linear part represent the best measurement condition. The tools are the underexposed area and the shoulder are the overexposed area. Film is developed automatically and does not require a developer or installer because the radiochromic film has no particle and is very accurate. It can be used for dosimetry in high dose gradient regions, such as near the barochrotherapy series and dosimetry in the major dose field. Has better energy characteristic, insensitive to environmental condition, although excessive humidity should be avoided. The response of the film does not depend on the energy and type of radiation, electron, gamma ray, or X-ray radiation, and dose rate, which is about 1030 gray per second. It used, it used to control the gamma process and low energy and high energy electron radiation. Now, a dose determination. Step by step processes. The step 1, orient. Focus the film to the radiation beam. Then chemically treated and imaging reaction. In the case of radiography, the film is chemically treated. In the case of radiochromic hysteresis, the time after exposure will be delayed as the imaging reaction occurs. Then read. Read the film on the calibration scanner. This will measure of the optical density. Then convert optical density absorbed dose by titration. The optical density, the log base 10 of the fraction of light transmitted through an exposed film to the light transmitted after exposure. I naught equal is the light collected without film. I equal is the light collected after passing through film. T equal is the transmittance. The ratio of the light transmitted through film to the light transmitted without film. The H and D curve is used to correlate exposure or dose to optical density. H and D curve. Film speed, fast film will have a higher dose optical increase in optical density, but will also have a limited optical density range. Slower film will provide better dose range and resolution. Faster film are more suitable for reduced doses for photographic purposes. Regression, the slope of the curve in the linear regions. Fast film have higher level. Latitude, the exposure range of the linear areas. This is also called scope. Linear area, the optical density is proportional to the exposure record. Toes and shoulders. These areas are not clinically useful because the relationship between exposure and light density is not linear. Fog, the film become dark due to background radiation or exposure to light. For X-ray film. Pace, the natural attenuation of the film without overexposure or fogging. There are 6 medical applications. Ophthalmic applicator dosimetry, brachytherapy dosimetry, interface dosimetry, stereotactic radiosurgery dosimetry, dosimetry in the beams penumbra region of radiotherapy, and hot particle dosimetry.
Now I will continue after abdel-baset with medical application. For ophthalmic applicator dosimetry, the calibration of ophthalmic instruments should be based on the determination of the surface area of absorbed dose, and the relative dose rate of the water in the associated profile should be determined to determine the two levels. The dimensional dose distribution produced by these applications due to the very high dose rates produced by these applicators. Radiochromic film has been proven to be ideal reagent for these analyses as demonstrated by the series of NIST. Radiochromic detectors are used to determine the surface dose rate and dose distribution of these sources. Due to its high surface dose rate from 0.1 to 1 gray per second and low sensitivity, approximately 104 grays for an optical density of 1. The detector can be used for this application as a radiochromic detector. The film was evaluated on an HENE scanning laser densitometer with a resolution of 0.3 micrometer. A comparison with the measured value of the NIST extrapolated ionization chamber shows that the consistency of the surface dose rate is within 6%. These films are used to map the dose difference readings the film with a laser densitometer. The absolute linear resolution of the system was found to be less than 1 micrometer accurate. They calibrated the radiochromic film with a good specification of cobalt-60 gamma rays. To verify this, the titration was carried out with cobalt-60 gamma rays and deuterium-90 beta particle. For brachytherapy dosimetry, the dose gradient around the bioluminescence processing source is very steep. The high spatial resolution provided by thin film dosimetry is superior to other detectors, such as the thermoluminescence dosimeter (TLD). Radiochromic film application for dosimetry near brachytherapy sources use a radiochromic film to distribute the dose distribution around the highly active chemotherapy 370 gigabecquerel to the iron 192 source. Now for interface dosimetry at the mental tissue dental interface. Radiochromic film is to study the soft tissue or water dose enhancement near high electron density material. Tooth restoration 18 karat gold alloy coating AGHD dental amalgam, and for NICR dental casting alloy the structure of a human natural teeth. An interlocking of stack of calibrated thin film radiochromic dosimetry and tissue stimulating polymer is used for these measurements. The polymer dosimetry stack on both sides of the dental material is irradiated with cobalt-60 gamma rays or 10 million volt X-rays, perpendicular to the material interface in a fixed direction. So that resulted that the dose enhancement in tissue was increased by the factor of 2 on the back diffusion site adjacent to gold and by factor of 1.2 on the dental tissue site, but was negligible on the anterior diffusion site. For stereoscopic radiosurgery dosimetry, radiochromic film is to study the effect of electronic imbalance in the small field used to irradiate intracranial region. The dose of the central axis gradually decreases for the radius of less than 10 cm. Using the radiochromic film can provide valuable high spatial resolution information for acceptance testing and dosimetry quality control and or for calculation. When the detector is too large, this produces a measurement result, which is easy to see the ionization chamber. Radiographic film and radiochromic film were used with an optical density assessment to provide the accuracy required to measure the absorbed dose of narrower beams. Now for dosimetry in the beam penumbra region of radiotherapy. Radiochromic film is to investigate any possible distortion in the marginal dose distribution due to the change in the energy sensitivity of the silver bromide film. The standard radiographic film was used for shadow measurement, and separate experiments were performed using fluorescent film and thermal incidence dosimeter to verify that the edge dose distribution distortion due to the change in the energy sensitivity of the silver bromide film was insufficient. For hot particle dosimetry. Hot particles are a problem in the environment of nuclear reactor because they represented a potential source of harmful radiation exposure for nuclear water. This work is also a preliminary demonstration of the possible high-resolution dosimetry using a radiochromic film. At 60 Celsius degree, preliminary result of measuring the dose distribution in the epidermis of hot particles, which are a micron-sized particle containing radiochromic substances. Now, the last part of this presentation is the future work. In the past, measurements made with radiographic film sealed and opaque and airtight vacuum tube always showed a change in the dose distribution from 5 to 10 millimeter before the depth dose of 1 curve. This is partially due to the inevitable small bubbles in the film shell at the edge of the film, that is, on the water surface. The accuracy of the radiographic film experiment may also be affected by the low energy electrons affecting the first 5 millimeter of the surface effects. Using a thin film perpendicular to the beam direction is an option. But these measurements are time consuming and the information collected is limited. So this setting is not preferred method. Rotating the electron beam with respect to the film plane within 4 degrees is also greatly reduce the impacts, which is very practical. Future works may provide calibration curves from advanced electrons beam dose calculation. One-dimensional and two-dimensional detectors array systems based on ionization chamber are still being developed to improve those measurements. Layers or MOSFETs have an advantage of improved spatial resolution and faster detector response. This makes it easy to detect the dose of each pulse signal. However, all of these reagents have a great limitation in terms of applicability, energy dependence and directionality of placebo, and the conversion of these reagents from the reading to the dose is complicated. For radiochromic film is a good alternative because it has a wide range of application in ghost image and has a higher spatial resolution than other first and the second dimensional dose detection system. The conversion from reading to dose is easy to solve. In principle, a simple calibration curve for dose reading is sufficient, but attention must be paid to the non-ideal water equivalent of the film. However, online reading is impossible, and attention must be paid to the growth effect after exposure. Radiochromic film dosimeters are used clinically as absolute dose detector to ensure the quality of IMRT and VMAIT irradiation technology, free filter application, and comprehensive testing. Whether the film can be used as a dose detector for MRI-guided radiators, MRI-done view array Electra is under investigation and has not yet been verified. For P0 equal 0.35 Tesla MRI, the first internal measurement showed no effect on reading the fixed P0 in the film, regardless of this direction of the film relative to the magnetic field. From these preliminary data, it seems that the thin film crystals containing dipole polymers are not affected by the 0.35 Tesla magnetic field strength. So, the thin film retains its properties. For the field of 1.5 Tesla used in electron MRI accelerator, no systemic research has been conducted yet. In addition, the membrane is also used for proton and heavy ion dosimetry. The main problem here is the difference in amplitude of bright peak detected between the membrane reading and the ionization chamber. For both protocols, conversion of reading to doses require additional research. The accuracy of determining the absolute dose of EPT3 film must be determined of radiochromic film dosimetry. So far, in volume MC of dosimetry uncertainty has reached the order of 2%, which is worse than the first generation EPT film. This is not inaccurate as a standard of 1.5% or better. The shortcoming of the film composition, such as film crystal size, the number of monomers of each crystal, mutual orientation, the amount of dye added by crystals, the stability of the dye-monomers ratio, and the water layer of the sensitive layer and the supporting layer all can play a role here. They are all an example of the shortcoming of the film composition. The recently result of EPT-XD film aims to reduce the influence of light polarization caused by the film-on-film readings. The reading system also affects accuracy. Flatbed scanners are also cheap and provide 3-color data, but they are not specifically developed for accuracy measuring film dosage. The creation of these scanners will cause system errors in the read signal, but fortunately this error can be corrected. The scan driver may also be prevalent the program providing the manufacturer for making colors copies of photo is not always the best. Also, for the physics behind radiochromic film must be understood, and the flatbed scanner reading must be checked regularly to maintain the accuracy of the film dosimetry. The data in the literature is of limited values because each scanner has its own characteristics. How to maintain constant quality within and between patches and how to ensure this. There is no literature on how to clearly verify the quality of the film, and there are no available specifications and restrictions. So the researchers are trying to develop this method for the first time, but its effectiveness has not yet been verified. In clinical practice, it's still necessary to consider the influence of the batch number, that is, the batch manufacturing processes and film type. And over the year, the quality of EPT3 film has improved, which is reassuring the dosimetry application of radiochromic film in a small equipment. This part deserves special attention. But at this time, absolute film dosimetry requires considerable labor to be applied in practice. Here, the department must make a strategic decision about the priority and deployment of the workforce. We can conclude that to help organize implementation of film dosimetry, the AAPM working group is preparing a new guidelines. However, this working group was hampered by the sometimes conflicting result of the film dosimetry study, and it has a difficult to make recommendation. The result is that the dosimetry absorption on the film is limited. So more works need to be done to understand the physics behind the film dosimetry, and the basic problem involves in the conversion of the film reading into doses of whatever substance is needed, such as a heavy metal is nearby the lung tissue, bones, and hip replacement. Even in Z effective value of the film and water are very close, electron beam experiments show that the change in the electron scattering behavior between materials must be clearly considered. Also, these differences in water are often ignored in the clinic. They warn that the conversion to dosage is complicated. But now the availability of radioactive film on the market need to be more addressed. As an EPT's film supply experiences show, film development and production must bring profits to the manufacturers. The disappointing level of clinical use may boost the bulk price of the film to unrealistic amount, risking development or even discontinuation. But currently the availability of very useful dosage reagent is highly dependent on the success of a single manufacturer, and there are no alternatives on hand. Thank you everybody for listening. It was presented by, at the first was Shadi Al-Amarat, at the middle was abdel-baset Ben Yassin, and in the end it was me, Usaid Al-Shurman. I have put some references here for this work. Thank you. I hope I have got you more useful information, and it was very good experience. Thank you very much.